Hi and welcome back to my channel. In this video we're going to be talking about LP modeling for bipartite matching. So what is bipartite matching? We talk about bipartite matching when we have subset of edges such that any pair in the subset does not share a common vertex. So let's consider these edges. Let's have this as an example, right? So we have this goes from here to here, this goes from here to here, this goes here, this goes here, probably this goes here. So let's pick another color. So this goes from here to here, this goes from here to here, and let's say this goes from here to here. So for bipartite matching, we want to find the subset of edges such that any pair in the subset does not share a common vertex. So what does that mean? This means that let's label this a little bit. Let's say this is 1, everything here 1, 2, 3, 4, 5. So for a subset of edges such that any pair of the subset does not share a common vertex, this means that we see that this and this share a common vertex here, right? So that means we're going to choose one, and when we choose this and this, we won't choose this and this. I don't know whether that makes sense. So independent pairs would include in blue 1, 2, 3, because they are independent. They do not share a common vertex. In blue, this edge is 1, 2, 3, but 4 and 5 in blue are not independent because they share a common vertex. This point, they share a common vertex at this point, right? But in red, we would only go with the edge at 4 because this is independent. These share a common vertex at 2. I hope that makes sense. So now let's look at how to represent bipartite matching with LP modeling. What would be our objective? In LP modeling for bipartite matching, our objective is going to be to find the maximum. We want to find maximum sized. We want to find maximum sized subsets. We want to find maximum sized subsets of edges such that any pair in the subset do not share a common vertex. So our goal when we use LP modeling for bipartite matching is to maximize this subset of edges that do not share a common vertex. If you have not subscribed to this channel, please do subscribe. It's totally free. So in LP modeling, it's going to look like a 01 IP. And this is because for edges, let's call our edges. For edges EI, would express this henceforth as X subscript I. This would mean edges. If it's chosen, we would represent it with 1, and if it's not, we'll represent it with 0. And like I said before, this is our objective. Our objective, I can write it down again. Our objective is to maximize the edges x1 plus x2 plus x3 plus xn. So this will be our objective. And the next thing we consider right now would be our constraints. What will be the constraint? For a bipartite matching situation, the constraint would be that some of the edges would share a vertex. But if we are going to represent that, that should look like this. So this is a constraint. We have this vertex, but then it's connected to edge 1, edge 2, edge 3, and so on. So because this is subject to edges that don't share vertices, so it means that for this kind of situation, we are only going to choose one edge, and this would also mean that that edge we have chosen would be represented as 1, while the others will be represented as 0. So that means that for this, we can say, remember we are going to represent EI with XI. So this means that for this, we can say X1 plus X2 plus X3 would be equals 1. This is what it means. And that's because we are choosing only one. And any one we choose would be represented as 1, and the other two will be represented as 0, since they are all connected to one vertex. I hope that makes sense. So to represent this mathematically, we can say we have XEI plus XE2 plus X. So where XE is just another representation for the edge, so this would either be less than 1 or equals 1. So let's take another example. So let's look at this diagram. This is an example. We have a diagram. Let's call this vertex 1. Let's call this vertex, let's say this is vertex 2. And we have vertex 3, and we have vertex 4 somewhere here, and we have vertex 5. So we have this line going from vertex 1 to vertex 3, and from vertex 3 to vertex 2. We have another line going from vertex 1 to vertex 4 to vertex 2 again. And we have another line going from vertex 1 to vertex 5 to vertex 2 again. So remember, our objective is to maximize this all the way to xn. So this means that for vertex 1, this is how you're going to represent this mathematically. This means that for vertex 1 goes from, okay, we could also label the edges. Let's call this edge 1. Let's call this H2. Let's call this H3. Let's call this H4. Let's call this H5. And let's call this H6. So that means that for vertex 1, and we can see that vertex 1 is connected to edge 1, H2, and H3. So this would be represented as X1 plus X2 plus X3 less than or equals 1. We have vertex 2 would be expressed as, this is vertex 2 connected to x4, x5, x6. So we have x4 plus x5 plus x is all less than or equals 1. Again, we have vertex 3 connected to only edge 1 and edge, this should be edge 2. So you have x1 plus x2 less than or equals 1. And we are going to continue all the way to vertex 5. This would be x2 plus x5 less than or equals 1. Vertex 5 would be x3 plus x6 less than or equals 1. So having said that, we also remember that x1 can either be 0 or 1. So the next thing we consider is how to solve this. So solving this will take an exponential time, and I don't think that's very helpful. So we can consider solving this using a network flow. So since it's going to be hard to solve this problem, we can consider relaxing the constraint. And our constraint being that x is always 0 and 1, we can relax this to, when we relax our constraint, we can now, instead of having x as entirely integers, we can go from that to this. X is between 0 and 1, and this problem is just going to be a special case of network flow problem. And because we have relaxed the values for x, we can now solve it using an LP solver. So we have a lot of LP solvers online. So if you can search for, just on Google, LP solvers, you find one. This is the equation you enter. These are the inequalities you enter. These ones, everything here, are they are the inequalities you enter on your LP solver with your new constraint, and automatically it's going to solve it and then give you your answer. But before we end this video, I would say again, if you haven't subscribed, please subscribe. It's totally free. Let's look at a simple flow for this problem. We have bipartite matching, where we expressed edges as 0, 1. So it became a 0, 1 LP problem. And 0, 1 LP problems, just as we discussed in a previous video, are usually hard problems to solve. So we did some LP relaxation. And after the LP relaxation, we use an LP solver. You can find this online if you just do a simple Google search. I wouldn't be recommending one. So you use an LP solver to solve this. And what happens at this point is two things happen. You either get the best solution, or if you do not get the best solution, we can round this up. I would be talking about this and more depth in a later video. We can round this using an approximation algorithm. We can do some rounding, then we try solving again. We're going to end this video here. In our next video, we will continue with LP modeling for a different kind of problem. See you in the next one.